I'll go on mute.
Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I can see that we have a whole bunch of questions left over here from previous times. So let me try and start addressing some of these. The question here from Memes about knot theory. There's some question about what is knot theory and things about electron charges and knot theory, which is a little bit less clear. But let's first of all start talking about knot theory. And I realize I should have a prop for this. Let's see, I don't think I have a ready prop. What can I use as a prop? Well, I could, this is very dangerous. I could use some part of the computer cable here as a prop. Knot theory is about what does it take to make this knotted? What does it mean for something to be knotted? It means if you have an ordinary knot, it means if you pull on the ends, it doesn't just go straight. It's kind of twisted up in the middle. Now, it is an interesting thing that, for example, if you try to draw a knot in 2 dimensions, if you try and just draw a picture of a knot flat, you can't do that in general without having lines that cross over, that lines where the same line has to be in the same place on the page, 2 lines crossing over. But you can make a knot in 3 dimensions. Any knot that you have that's some line that's twisted up and knotted together, you can always, what's called in mathematics, embed that in 3 dimensions. You can always render that knot as something that exists in 3 dimensions. Now, actually, if you want to get very fancy math, you can go beyond that and you can say, imagine instead of having a line that's all twisted up, I have some whole surface that's all twisted up. How many dimensions do I need to go to so that I can embed that surface without ever having to have something where 2 things are at the same place? And there's a whole sort of hierarchy of sort of generalizations of knots that aren't just a single line being twisted up, but they are something like a surface being twisted up and so on. But that's a more complicated thing. Let's talk about ordinary knots. So the first question is, when are 2 knots equivalent? That is, what does it mean for knots to be equivalent? Well, it means that without untying the thing, you can just sort of, you've got 2 things where you say, this is how my piece of string winds around. But those two versions of winding around, you can continuously get from one to the other. You just move the string. You don't have to untie it. You don't have to, you don't have to kind of, you can keep the ends fixed in place, and you could just be messing around with the inside part. And so you don't ever have to get those ends and untie the thing and go back to something different. So the most trivial knot is usually called by mathematicians the unknot. And the unknot is something that isn't knotted. It's just like you have the piece of string and it's straight and there's no knot in it. The first non-trivial knot is a thing called the trefoil knot, which is, oh gosh, I'm not good at this, but it's the first way of knotting things together. And so one question is, are there only a limited number of knots, or are there an infinite number of possible knots that are inequivalent? So remember, knots are equivalent if you can just continuously deform from one knot to another. So the way mathematicians usually deal with knots is a little bit impractical, but it makes things a little bit simpler. When one deals with knots in pieces of string or rope or whatever else it is, it usually has 2 ends that are free and you're able to like pull on those ends. But for mathematicians, they usually join those ends together. So the unknot is actually like a circle of string rather than a straight line of string. And the trefoil knot is then a sort of a twisting of that circle. So there's a question of, for example, one basic question would be, are there an infinite number of knots? That is, can you just keep doing more sort of twistings of things that are inequivalent? The answer, yes, there are an infinite number of knots. That wasn't known. Even like 130, 40 years ago, that was not known, that there were an infinite number of knots. It was a whole classification of knots that was done. So for example, I think the early books of knot classifications were knots up to 8 crossings. So crossings means if you were to draw the knot in a plane, how many times do the lines cross over? And when, in general, when you draw a knot, you could have many crossings over, but there's a minimum number of crossings over. There's sort of a best drawing of the knot that has the minimum number of crossings over. And I think the early classifications have got up to about knot size 8. So now another question is, can you tell whether 2 knots are equivalent? If somebody just shows you, this is 2 configurations of string, what does it take to show that those 2 knots are equivalent? That turns out to be a really hard problem. It turns out that in general, let's see, I think, well, in the classification of mathematical problems, it is given a sort of a version of the knot where you just have straight lines and you're making the knot out of sort of straight pieces of string. I think the problem of determining knot equivalence is certainly what's called NP-complete. And yes, that's right. That's right. So in other words, there is to determine whether 2 knots are the same, it is sort of exponentially hard to do that. If you've represented the knot as so you've got these 2 configurations of string, and they're both represented just by these sort of discrete jumps. So you have a string going straight in the X direction, let's say, then it goes up in the Y direction, then it goes in the Z direction. So you've got a bunch of straight segments. And let's say you've got n straight segments, then in general, to determine whether these 2 knots are equivalent, you're essentially having to make a separate sort of move to each of those segments. And so it's sort of exponential in the number of segments to determine whether these 2 knots are equivalent. At least that's the best known algorithm. I don't think it's known for sure. Well, I think it's known. Yeah, I think it's known to be NP-complete, which means that if you could solve the problem of knot equivalence, you could solve a whole bunch of other problems in computational problems. So it's probably really hard, probably irreducibly hard, so to speak. But so first question is, are 2 knots equivalent? So a bunch of progress was made about 30 years ago now in this question of, are 2 knots equivalent? And what was done was there were a series of knot polynomials that were discovered, I should say. And so what that is given a knot with some structure, the question is there some aspect of that knot that will be unchanged in all possible deformations of that knot? And the answer is that there were these polynomials found which are characteristic of the knot itself and don't change as you deform the knot. So let me give you an analogy. So in topology, topology is kind of this area of mathematics that's about the general shapes of things. So in topology, there's this idea of the genus of an object. So for example, a sphere has genus 0. Genus is basically the number of holes in the object. So a sphere has genus 0, a donut with 1 hole or a torus has genus 1, a donut with 2 holes has genus 2. Okay, why is this relevant? Because the genus of an object doesn't really depend on the detailed geometry of the object. You can take the sphere, let's say it's a piece of dough or something, you can squash it any way you want. So long as you don't make a hole in it, it's still genus 0. But it is that these are topologically equivalent when anything which is sort of the thing without a hole in it is topologically equivalent to the thing to the sphere. And so it's the same kind of thing with knots. You're asking, when are 2 differently configured knots in a sense topologically equivalent? It's a little bit different notion, but it's the same general idea. And one way to characterize that, just like genus, number of holes, is a way to characterize the overall topology of things. So there are these knot polynomials that allow you to characterize the sort of the shapes of knots. And there are a few of these knot polynomials known, about 3 or so famous ones. And you might say, well, okay, so that will allow you to tell whether 2 knots are equivalent. But no, it doesn't work that way, because 2 knots that are inequivalent must have different knot polynomials, but 2 knots that are equivalent, two knots that are equivalent must have the same knot polynomial, but 2 knots that are different may not have different knot polynomials. So if there are 2 knots where they're just deformations of each other. They must have the same knot polynomial by the way that knot polynomials are constructed. But if you have two knots that are different, they might happen to have a collision in knot polynomials, so you can't tell that they're different. And so that's why even knowing about knot polynomials, which are a pretty clever idea, it doesn't give you information about this knot equivalence problem. So one question is, it's sort of interesting mathematics to study knots and knot theory, but there were reasons, for example, in physics, why people thought about that. And there was a theory about, but this was in the late 1800s and not 1880s. It was a very charming theory. So at the time, people thought that the universe was full of this thing that they called ether. Just like, in our atmosphere, there's air, it's a bunch of molecules bouncing around. And when we make a sound wave is compression and rarefaction fronts in the air. So when we talk, we're making sound, which is compression, decompression of the air going out in this kind of wave, and that's how sound is carried. People thought, in a very Victorian name, they called it the luminiferous ether, the light-carrying ether. And that was thought that there was this thing, they didn't really know how it worked, there was thought that there was this thing called the ether that was the thing that would carry light waves as air carries sound waves. And so it was thought that sort of the universe was full of such a thing. It sort of got the around 1900, this thing called the Michelson-Morley experiment kind of proved that in some sense there wasn't anything really quite like ether, and that's what led to the invention of special relativity and so on in 1905, etc. But and needless to say, in the way that science often works, there really are things rather equivalent to ether that exist today in the universe, but that's a different story. Anyway, back in the day, 1880-ish, people thought there was this thing, the luminiferous ether, that sort of was throughout the universe. They also were just discovering atoms, and they were discovering that the different chemical elements were all different kinds of atoms. They didn't know what was different between those different kinds of atoms. That waited another 30 years or so before people started understanding about protons and neutrons and different atomic nuclei and all those kinds of things, to understand what was the difference between a hydrogen atom and a lead atom or something. What was the difference between those things? So it was a very charming theory that maybe all these different kinds of atoms are just different knots in the ether. Maybe these atoms are the way that matter exists is as sort of this knot in the ether. And so that started, just to fill in, for historical interest, I mean, a person called Kelvin, William Thomson was an inventor. Also, the Kelvin scale of temperature is named after him. He was one of the people involved in this. Another one was James Clerk Maxwell, who was the creator of Maxwell's equations for electromagnetism. Those two were big on this idea of atoms might be knots in the ether, and so that might sort of reduce the problem of why are there 92 elements, let's say, or whatever. Why are there this number of distinct kinds of atoms? Oh, it's because there are a certain number of distinct kinds of knots. They didn't know there were even, at the time, they didn't know there were an infinite number of distinct possible knots. And so a childhood friend of Maxwell's, actually, named Tate, was the first person who started classifying knots and tried to figure out just how many different kinds of knots there were, because people thought atoms might be things like knots. Now, needless to say, in the way that that theory was sort of discredited, and people said, no, actually atoms are made of protons and neutrons and electrons and so on, and the luminiferous ether doesn't exist, and that's all gone. It turns out in our now that we understand in our recent theory of physics that we understand a lot more about how space and time is created and so on, particles like electrons and so on, they're not quite knots in the structure of space-time, but there's something a little bit like that. Which we don't yet understand completely, but they are essentially topological obstructions, so to speak, in the structure of space-time. Well, knots have had a whole long history in their use in physics, for example, and other areas. Sort of, it's a big question for DNA, for example. It's a long, our DNA is like a whole meter long. Each DNA molecule inside our cells, if you just pulled it out, it will be a meter long thing, but it's curled up very tightly inside each cell in our body. And when it curls up, there's sort of questions: does it get knotted? Does it not get knotted? There's a bunch of issues there. There also are questions. It turns out, okay, so this question of sort of how things exist. Okay, this sort of topological question. Let me give you an example. If you have a fluid like water, you can have a vortex in the fluid. You have this little whirlpool that's going in the fluid, and the whirlpool lasts quite a while. If eventually the sort of the internal friction in the fluid, so-called viscosity, will damp out that vortex. If it wasn't for viscosity, the fluid will just keep going around in a line, like in a circle like that. And so the center of that vortex is a tube that is essentially a line. So effectively what's happening is in the fluid, there's this thing that's going around in a circle, and defining where that going around the circle goes, there's the core of the vortex defines a line. So one of the questions you can ask is, could there be a knotted vortex tube in a fluid? And I think such things were recently produced, very recently, last year or two. People finally managed to make kind of knotted vortex tubes in fluids, where you can have, like, when you have a smoke ring, for example, if you like make a smoke ring, you can that's a vortex. That's a slightly more complicated kind of vortex. That's a toral, a motion of the fluid that's in kind of a torus shape. Again, it's using this kind of ideas of topology to have something which is a stable structure that in the fluid. And there are other places where you can get these kind of knots and things potentially forming. For example, in the early universe, you can potentially have it. That's actually getting us in a complicated story there about the kind of the formation of kind of areas of the early universe that have different structure and have sort of topological defects that are associated with things like vortices. So that was a very brief description of knot theory and its life and times. Knot theory has become it's a slightly off the beaten path in some ways thing in mathematics, but it has many connections that have been found to some very core ideas in mathematics to do with geometry and topology and so on. Okay. Let's see. Questions here. Okay, there's a question from Heather here. Why does computer code involve math? Why isn't it just a set of linear instructions that sometimes hop around, like kind of choose your own adventure book? Well, so there's a big question about how we should tell computers what to do, because any computer has a certain set of built-in instructions, a certain set of built-in things it knows how to do, the so-called machine code of the computer. And their typical computers might have a few hundred kinds of operations that they intrinsically know how to do. Like they intrinsically know how to add two numbers together. They intrinsically know how to take a piece of data and store it in a certain memory location in the computer. They intrinsically know how to get something from a particular memory location in the computer and then add it to something else and so on. So there's a question of when we tell computers what to do, how close are we to that machine code of what computers intrinsically know how to do? And I've spent a large part of my life trying to build computational language, which is kind of more on the human side than it is on the how the computer is built side. That is, it's more on the how do humans want to describe things in computational terms than it is about how the computer intrinsically knows how to do those particular kinds of operations. And so a very good example of that is, let's say you have a list of numbers, just got 100 numbers, list of numbers, or a list of images, doesn't really matter, list of things. And you want to do an operation on each one of those things. So in our language, in Wolfram language, the way you do that, you can take any operation, let's say it's image, and you want to, I don't know, turn it upside down. There's some function image reflect that would do that, or image rotate, whatever that would do that. And so what you do is, in our language, you just say, take that image rotate operation and just apply it to this whole list. Map it across this whole list. Just in one gulp, you, as you think about it, are just saying, I want to apply image rotate to this whole list of things. I want to map it across this whole list of things. Okay, I'm done. Okay, so if you are thinking about what does the computer actually do to achieve that, well, the answer is the computer goes in a loop. It says, let me apply that operation to the first thing on the list. Okay, I've done that. Let me apply it to the second thing on the list, third thing on the list, and so on. It goes through this whole series of operations to apply things to different parts of the list. Now, what I believe is that the best way for humans to kind of get the furthest in thinking about how to compute things is all they have to think about is, I'm mapping this function over the whole list. Boom, I'm done. Not, oh, I've got to make this thing which goes this thing to this thing to this thing, and eventually I'll reassemble the whole list out of these pieces that I've made, and then that's what we have. But so when you think about what is the computer actually doing inside, well, it's kind of complicated. It's got to say, well, I'm starting off with, I've got the initial list, and I've got the final list. The final list has nothing in it initially. The initial list has 100 things in it. Then I've got this program that says, pick up the first thing, do my operation, put it in the new list, pick up the second thing, do the operation, append it to the new list that I've got. It's kind of a messy, complicated thing. And in the instructions in the machine code of the computer, it's probably a whole bunch of instructions in the machine code to do this kind of thing. So a very common type of operation that one does in computers is to say, do this, then do this, then do this, then do this. But the thing I just described is a loop. It says, do this, then do the same thing again with some small change, like do the same thing again, but now it's being done to the second element in the list, the third element in the list, and so on. And so it's a very common mechanism that exists in the machine code of computers to be able to do that kind of looping. How is it achieved? What's happening is the program that the computer is running is just like data stored in the memory of the computer. But that data, instead of being like, for example, a table of numbers or a piece of text or something, that data that's stored is, it's the machine code, and it is stored in the form opcode operand. So the opcode might be operation number 700, well, operation number 15, let's say, is add two numbers. So it'd be like a 15, and then it's like the first number to add, the second number to add, or the locations in memory to get the first number and the second number, and so on. And so that is like data, could be, if you didn't know what it was, it just looked like a bunch of numbers, but actually it corresponds to a program to tell the computer in machine code what to do. And so it's, as the computer then executes that program, it has to say, it's going to go down line by line through that program saying, now I do this, now I execute this opcode. Now I go to the next line, and I execute this opcode. Okay, so there's a thing called the program counter, which is basically a thing that says, which place in this program are you now executing? So the typical thing is that the program counter just goes up by one. So it executes one step in the program, then it goes up by one, executes the next step, and so on. So there's this notion of jump instructions, which say, change the program counter. You just reached the end of this sequence of instructions. Now go back 5 steps with the program counter, reset the program counter to the program counter -5, and then it will start recomputing those things again. So a typical, very typical thing is operations like existed even on calculators, decrement skip on 0. So that means you'll have some variable, some place in memory where you're storing a number, and you'll get to this instruction that says that is a that just subtracts 1 from that number you're storing, and decrement skip on 0 means you usually would just subtract 1 and then you do the next instruction. But decrement skip on 0 will mean if you subtract 1 and the answer you get is 0, then skip the next instruction and go to the one after that. So it's kind of messing around with a program counter, and it's telling you how to do that. So this is unbelievably low-level operations of computers. This is how the wiring, the low-level electronics of a computer works. It is far away from the way that people, I think, should be thinking about how to interact with computers. Although it is a shocking fact that most of the programming languages are still operating at the level of tell the computer exactly what to do, go through this loop, append things to a list, rather than this sort of higher level way where it's like, yes, the person can understand what the computer should do. Now it's up to the people who build the technology to make that all just work, rather than the human having to go way down to the level of the computer, so to speak, and say, this is the detail of what you have to do. Now, the question here is, so what are, like, for example, let's take this question about how you're dealing with elements in a list. What do you do with elements in a list? So one thing you can do, what are the sort of high-level operations that you can do with something like that? So one high-level operation is to say, let's apply this function, let's say image rotate, to every element in the list. That's mapping across this list. Another thing you might do is, let's say it's a list of numbers that you have. Another thing you might do is to say, take some function and just use all those numbers as inputs to the function. So let's say the function is plus, then you're just using all the numbers in the list as inputs to that function. Okay, so that whole list is just plus, 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 plus. It just all compresses to the sum of those numbers. So that's another kind of operation, usually called applying a function to a list. So then there are other kinds of operations that you can do. Like here's one that's a little trickier. This is essentially an accumulate operation where you say, I want to take a list, and let's say it's got numbers in it. And what I want to do is I want a new list that is always the cumulative sum of the numbers in the previous list. So what you're doing is you've got your first list, and then the elements in the second list, you're saying the first element is just the first element of the first list. The second element is the first element plus the second element. The third element is first element plus second element plus third element. That operation is usually called folding a function into a list. And so there are a series of these kinds of operations. And this is the story of so-called functional programming, is the construction of these kinds of operations where you're taking a function and, for example, doing things to a list. The thing that is, let's see, I'm confused by something here. Okay, the thing that is sort of a way to think about computation, this kind of idea of functions being applied to lists and how that all works. That's the story of functional programming. It can be a little difficult to sort of wrap your brain around at first. Once you get it, it's incredibly powerful. And for example, for me, I just think in those terms and I can just start typing. It's, a fold list of a nest list of whatever. I don't really have to think in detail. I never have to think about what's happening with the individual elements of the thing. It just sort of it's just, I think of it in kind of one go. And that's a very powerful thing to be able to do. That's kind of the story of the sort of higher level description of the computational process beyond the level of do this, then that, and make a loop and so on. All right, there was a question here. Question here from Mikhail. What type of computer logic is the most efficient? Binary, ternary, etc. Oh, interesting you asked that question, because I was literally just wondering about that yesterday. Tell you a story. So most computers, they operate, essentially all modern computers operate in binary. What that means is you take a number like 7, for example, and you represent that not in base 10, let's say number 17, for example. You represent that not in base 10, but in base 2. So 17 is 7 ones plus 1 10. Okay. In base 2, let's say 7 would be equal to 1 1 plus 1 2 plus 1 2 squared, which is 4. And so 17 would be equal to, well, it's 1 2 to the 4th, which is 16, plus 1. Okay, so, and you can represent any number as any integer, for example, as just a series of zeros and ones, where you're taking, it's a positional notation where the position of the 1 is telling you, is there 1 2 to the whatever or not? Okay, so that's the way computers tend to represent everything. It's just in binary, in sequences of ones and zeros. Okay, so when a computer has to do operations, it has to take these things represented in binary and do operations on those binary bits. And so the standard operations that are done are the operations of Boolean algebra, which are the operations of logic, which are things where you equate, where you consider 0 to be false or off, and 1 to be true or on. And then you say, if you combine two things, you can say the and of them, which means are they both true? Is A and B both true? So that means that true and true is true, but true and false, that's false. Or you can have or, if it's true or false, that will still be true. And true or true, it's still true. False or false, that's false. So it turns out that you can make up sort of arbitrary logical operations by combining ands and ors and nots and so on. You can also do it by combining just one operation called NAND. NAND is not and. I don't think any human language has a single word for NAND or has a sort of everyday word for NAND, but it's the not of the and. So if you say, let's see, I can't do this in natural language, but something like it's raining, NAND, it's sunny. So that means that is actually that's a yeah, okay. Is it raining? Is it sunny? Those are both things which could be true or false. And the NAND of those things is the not of the and. So it's not both raining and sunny. That's what NAND of that would mean. So it turns out that just by combining lots and lots of NANDs together, you can make all these different operations. So for example, let's see, takes me a while to figure this out. I think that, like, for example, I think OR is a combination of like 6 or 7 NANDs altogether. NAND of, if you have P and Q, it's, NAND of P and Q of NAND of Q of P of et cetera, et cetera, et cetera. When you work that all out, it comes out to be P or Q. So anyway, you can make everything out of NANDs. And it's the mathematical terminology is NAND is functionally complete. Sometimes somewhat confusingly, it's called universal, but that's a different meaning from the sort of more formal meaning of so-called universal computation. So in any case, and why is it important to know that NAND is functionally complete? Back when it was first discovered in 1900 to 1910, it was kind of a curiosity, though people got enthusiastic about it. The reason it's relevant today is that computers are kind of all NANDs. The individual operations on the microprocessor chip are all, actually, they're usually NOR operations, which are just like NANDs, but they're a little less famous. But they're basically like a billion NAND operations, all combined in different ways to make all the operations of logic as we know them. Okay, so that's how ordinary computers work. Okay, so the other possibility is, instead of just saying everything is a bit, 1 or 0, you could say, let's have things be what is sometimes called trits, ternary bits, where it's 0, 1, or 2. Or you can think of it as -1, 0, and 1 if you want to. And that would be like thinking of a number in base 3 rather than in base 2. And so then the question is, can you make up logic that is like the analog of AND, but and the analog of NAND and so on for trits instead of bits? And I have to say, I do not immediately know how that works. And I don't know immediately what the functionally complete operations for ternary logic are. And I was just thinking about this yesterday and thinking I should write the very simple program to find that out. Part of the reason I was thinking about it yesterday is because I was trying to track down the history of some particular kind of ideas. And that history finds its way through the Soviet Union in about 1960-ish timeframe. And it turns out that in the Soviet Union, there were a bunch of computers made that were ternary computers, that were computers that were based on this 3-level logic. And those computers, I think it was one called the Saturn or something, was made around 1958 or so. It was a fairly early computer. And there was a period of time when basically computers in Russia tended to be used base 3 rather than base 2. That kind of decayed. Eventually, they started copying American IBM 360 computers, and that no longer was, the ternary computers kind of went extinct. But the question still sort of remains. People said mathematically the ternary computers were really interesting, but I don't know enough about them, so I can't really say whether that's a good way to do things. It was certainly said that it was, and I just don't know. I haven't worked it out. There's a question from Leonardo saying that all Boolean functions can be constructed from NAND. Is it true from any other simple Boolean function? It's also true of NOR. NOR is kind of trivially related to NAND. So for 2 input Boolean functions, there are only 2 functionally complete. There are 16 possible Boolean functions with 2 inputs, and OR and NOT and XOR and so on and so on and so on. There are 2 inputs, and for each of the 2 values of those 2 inputs, that's 4 possibilities, there's 1 possible output. So that means there are 2 to the 4 possible complete functions, or 16 possible functions. And of those 16 functions, 2 are functionally complete, NAND and NOR. So now you can ask questions like, what about 3 input Boolean functions? And actually that was a person named Emil Post, who we happened to be about to do a kind of centenary celebration of something that he worked on, Post's problem of tag, next week. Anyway, Emil Post was interested in the 3 input Boolean functions, and worked out a little bit about when were there functionally complete 3 input Boolean functions. Actually, I worked on that, and then completely independently, my youngest son worked on that, not knowing that I'd worked on it. And I didn't know that Emil Post had worked on it until sometime later. So it's been looked at several times. And the answer is that there are, of the 256 3 input Boolean functions, there are a bunch, like 15 maybe, that are functionally complete. And as you go, and there's some that are more efficiently functionally complete. NAND and NOR are basically equivalent to each other. And the ones for 3 inputs, they're a little bit more, there's more diversity in their functional completeness. And I think Christopher worked out which one is most efficiently functionally complete. It's actually not an easy thing to work out. But you're basically asking, what is the size of program made from the 3 input functionally complete thing that reproduces all the 256 possible Boolean functions with 3 inputs? And you can figure that out. I asked him, what about the 4 input one? He said, that's too hard. At least that was a few years ago. So maybe it's possible now. But for 3 inputs, we do know what the most efficient one is. But what happens is you go to more and more inputs, the fraction of functionally complete functions actually is like, I think it's eventually like a quarter of all functions are functionally complete. So that's how that works. I don't know the answer for the I know it for multiple input 2-level functions. I don't know the answer for the 3 input functions. Although now that I think about it, I think in my book, New Kind of Science, I talked about the 3 input logic case, and I'm now realizing that I think there's a very good chance that there's a note in the back of that book that has the answer to this question. That book is today actually is its 19th anniversary of its publication. So that means that whatever work I did on this was probably 25 years ago. And I remember a page of that book that is about multi-level logic, but I don't remember what the answer to this is. There's a question here from Aman. How does NAND realize NAND? Well, it's very easy. NAND is already NAND. So you don't have to worry about how you make a NAND out of NAND. But it is the case that many combinations of NANDs simplify to just a single NAND. So you can have, and I cannot possibly do this in my head, but like, for example, it could be that NAND of P and Q, the NAND of that with Q of the NAND of P and Q and so on. When you untangle that, it just comes out to be NAND of P and Q. So there's an infinite collection of expressions. See, let me give you an analogy. Let's say that you have algebraic variables, X and Y, and you're trying to make the expression X plus 3Y, for example. Well, you can make that by saying X plus Y plus Y plus Y. You can say it by making X minus X plus Y minus X plus Y plus Y, something like that. There are actually an infinite number of algebraic expressions that you can make that all simplify to the same, that all have the same value, X plus 3Y. And the same thing happens with NANDs. You can have this sort of infinite collection of sort of nested NANDs and so on that all collapse down to just NAND of P and Q. So it's sort of the same way that works. Okay, let's see. Well, there's a question here. Question from Simple. Why are we only considering first-order derivatives of position, velocity, and second-order acceleration? Why are higher derivatives not relative, apparently? Okay, that's an interesting, that question has a much stronger sting in its tail than you might have imagined. Okay, let's see if I can untangle that. So the first question is, let's say, so this is sort of the part of the basic story of calculus. There's this idea, I'm at this position. Okay, great. Position, call it X. It's, you know, I'm at position 3.7. I've got a line and I'm numbering off where everything is. I've got my position X is 3.7. Okay. Now let's say, imagine that position changes with time. Okay, so we're asking, how fast does that position change with time? How long will it take me to get to 3.7 plus a little tiny bit, 3.7 plus another tiny bit? So that's asking me the rate of change of X with time. And the rate of change of position with time is velocity. That's telling me how fast am I going? How much am I changing my position per unit of time? Okay, so that's velocity. So then the next thing we can ask is, okay, great, we're changing our position as a function of time. We can also ask, how fast are we changing, how fast we change our position as a function of time? That's the so-called second derivative of the position. The velocity is the first derivative, the first rate of change of position with respect to time. But now we can ask, what's the rate of change of velocity with time and that acceleration? So in principle, when you put your foot on a gas in a car, it's accelerating the car. It's making the car, it's putting more force into pushing the car forward. And Newton's second law says the force that you push something with is its mass times its acceleration. So it's saying you put force on something and it causes acceleration. It causes the velocity to change at a certain rate. So you keep putting that force on something. Let's say this is, you're trying to make some starship go to the next star. If you just keep putting the same force on it for a long time, for a year, you keep making something accelerate, it's going to be going really fast at the end of that year, because it's just progressively increasing the velocity as a function of time, because you're pushing it with that acceleration. So position, velocity, acceleration, all widely used, widely studied. We talk about them all the time. The next derivative, the third derivative, is the rate of change of acceleration with time. How much does the acceleration change with time? So for example, let's say you're putting your foot on the gas in a car, and let's say you are gradually putting your foot on the gas. As you push your foot on the gas, it increases the acceleration of the car. But as you gradually put your foot on the gas, the rate at which you put your foot on the gas, that's the rate of change of acceleration with time. Now, the thing that's most common is when you have a rapid change of acceleration, and usually the name for that is, it's usually called the jerk of how much does something jerk? How much does it, the rate of change of acceleration is like, when there's a high rate of change of acceleration, it's like in a car, it's like it jerks you back or forward or whatever. So the rate of change of acceleration is this thing called jerk. It's often called jerk. It's not particularly widely studied. So now the question here has to do with, yes, okay, this question is a bit tricky actually. Okay, so fundamental fact known to Galileo in the 1600s is that, or believed by Galileo, is that in some sense, if you are moving at a certain velocity, everything can happen relative to you in the same way that would happen if you were at rest. So imagine you're in a train car, and everything's blacked out, and the train car is moving perfectly on a track at a certain velocity, certain speed. And you're doing all kinds of things in this train car, you're having your breakfast or whatever else. You can't tell as you dig into that piece of breakfast, nothing about you digging into that piece of breakfast can you tell any difference about the speed of the train car. It could be going at 10 miles an hour or 90 miles an hour, so long as it's perfect and you're not hearing a clickety-clack from the track or something like this. You can't tell as you're eating your breakfast, you can't tell how fast the train car is going. And that's a general principle that was originally talked about just in terms of ordinary mechanical kinds of things. The theory of relativity, Einstein's special theory of relativity, is all about how you can't tell even, it's that the speed of light will always appear constant. However fast you're going, if you're shining a flashlight, then you might think, oh, if I shine a flashlight and I'm going really fast relative to the universe or something, relative to my train track, then my flashlight would be the effective speed of the light is the speed of the train plus the speed that the light comes out at, which would be bigger than the speed of light. And so the key idea, which actually was part of Maxwell's equations, and then kind of the consistency of that was what came out in special relativity, was the idea that actually when you shine that flashlight, even if you're going really fast, half the speed of light, the light coming out of your flashlight will still only be going at the speed of light. How can that possibly work? Well, this was the idea of special relativity. The idea is that can work just fine if you redefine your notions of length and time. So in other words, that the light is coming out at the speed of light, but you're redefining there is a contraction in time, the contraction in length, there's a dilation in time associated with how fast you're going relative to somebody who's at rest. We can explain how that works. Actually, in our theory of physics, we finally have a very straightforward way to understand time dilation, to understand the idea that if you're going fast, then you're effectively, if you think about the way that you perceive time, it's about you are sort of, your brain is operating, your brain is kind of computing things at a certain speed. And in a sense, the way that that computation is working, it's changing things in the universe as a result of the things that you're thinking about in your brain. And what you realize is that when you move from one place in space to another, you're also changing things in sort of the way that in the structure of the universe. And you kind of have a choice. You can change things in the structure of the universe by moving to a different place in space, or you can change things by just evolving in time. And time dilation comes about when you're moving in space. You are effectively using up your computation in the process of that motion in space. And so you don't have sort of as much computation to use up in going forward in time. And so time, in a sense, appears to go more slowly for you because you already used up a bunch of the sort of computation that you might have used to evolve in time by moving in space. Well, in any case, so in relativity, there's sort of this idea that if there's no acceleration, if you're just moving at a certain velocity, you can't tell what velocity you're moving at. You can't tell about it with mechanics, you can't tell about it with electromagnetism, etc. You just can't tell. Okay, but as soon as there's acceleration, you can tell. Imagine you're eating your breakfast and so on, and the train car is suddenly coming to a halt. Okay, we all know then your breakfast gets thrown to one side of the train car. That's because, unlike with velocity, with speed, where you just can't tell, you're merrily going along and you're going at the same speed, and your knife and fork are going at the same speed, and you just can't tell what speed you're going at. As soon as there's acceleration, splat, you're on the, your breakfast is on the floor type thing. Okay, so the next thing that happened in sort of the history of physics was Einstein's general theory of relativity, and that involves this thing called the principle of equivalence. And the principle of equivalence says you can't tell the difference between the acceleration of the train car and your breakfast falling on the floor and going splat because of acceleration, and your breakfast falling on the floor and going splat because of gravity. In other words, if somebody had tipped the train car up and there was gravity was pulling your breakfast down in some direction, then that is there is no difference between acceleration and the force of, and the effect of gravity. Okay, so that's the principle of equivalence. The idea of so-called general relativity is this idea that a gravitational field is equivalent. You can't tell the difference between a gravitational field and acceleration. Okay, so now the question that's being asked here is, what is the analog of that for change of acceleration? Well, the answer is that the case of ordinary acceleration is the case of a uniform gravitational field. So on the surface of the Earth is big enough that the gravitational field is more or less uniform. It uniformly just pulls things down in a straight line towards the center of the Earth. But in general, the gravitational field doesn't have to be uniform. If we look at the Earth from a long way away, we'll see the gravitational field is sort of going out in all directions from the Earth. If we were to look at the gravitational field around a black hole, for example, an ordinary black hole that isn't spinning around rapidly has gravitational field that also just sort of goes out like a hedgehog. But a spinning black hole has a more complicated configuration of gravitational field that involves things like frame dragging, which is sort of a sort of a vortex-like thing in the gravitational field, and so on. So there are more complicated gravitational fields that you can get by having more complicated configurations of mass that produce gravitational field. And so what happens is, in a uniform gravitational field, that's where this principle of equivalence that says it's just like uniform acceleration. Okay, but in a more complicated gravitational field, you can have something that is like other configurations of acceleration and even change of acceleration and so on as a result of these more complicated structure of gravitational field. So something like the principle of equivalence would be true for this more complicated kind of configuration, but you would say, so the question is, can you invent a configuration of the gravitational field that will be indistinguishable from jerk, from acceleration of from change of acceleration? And so I think you could do that. Let me think about this for a second. Okay, so I suspect, let me think for a second. Well, there's a small effect of that. Yeah, okay. So there will be it won't be linear change of acceleration. How would you get that? Well, let me explain what I was thinking of. So on the surface of the Earth, the acceleration due to gravity, the acceleration that is the equivalent of the gravitational field, things accelerate at 9.8 roughly meters per second per second. So that means every second, things are going faster by 9.8 meters per second. So in principle, if you drop something from a big height, for a while it will keep going faster and faster and faster and faster. And every second of the time it falls, it will go faster by 9.8 meters per second. Now, that's not really how it works, because in air, there's air resistance. And so actually things reach a terminal velocity that isn't even very fast in the air. There's a famous experiment done by one of the Apollo astronauts who had a feather and a rock that he took to the moon. And the moon, of course, doesn't have an atmosphere. It's just a vacuum. And he drops the feather and the rock. And needless to say, they fall at the same speed. And that's fortunate, because otherwise there's no way a spacecraft would ever have gotten to the moon, because all the calculations are based on that idea. But in any case, so at the surface of the Earth, everything just falls 9.8 meters per second. But as you go further away from the Earth, the gravitational field gets less and less. And by the time you're at by the time you're far away, like at the position, or like let's say at the position of the moon, you go out to the position of, I don't know, Mars or something, the gravitational field, the gravitational effect of the Earth is pretty small by the time you get out to the position of Mars. It goes down like an inverse square law, 1 over the square of the distance. And so what that means is that acceleration that you get by something falling towards the Earth, that acceleration is changing as you get closer to the Earth, because the gravitational field, instead of it being 9.8 meters per second, it'll be, at some point it'll be 1 meter per second. Then go even further away, it's 0.1 meters per second. So that means there's a change of acceleration as you get closer to the Earth. That change of acceleration will not be, it'll be, according to this inverse square law thing, it will not be a linear change of acceleration of the kind that you would get from the third derivative of position. So the question is, what is the configuration of masses? What shape would the Earth have to have such that its gravitational field will produce a uniform change of acceleration, the uniform change of gravitational field as a function of position? And let me think how you'd work that out. Let's see, we need to invert, how to do this. Let me think. So I think, I don't think I can compute this in real time. I have this vague feeling that some conical arrangement of matter would have this feature, that somehow as you get, if you're in a cone, and as you're falling towards the apex of the cone, that you might have this effect, that you have just a pure sort of increase of acceleration with time, a pure so-called x triple dot, third derivative of the position. So in any case, so the answer is, I think that with a certain, it just doesn't happen to be a very popular configuration of masses that lead to a third derivative of position, but you certainly could make one, and you could be discussing it. And I think, yeah, that is just not one that really comes up very much in general relativity and the theory of gravity. But it could, in principle, that could exist. And you're asking why they're not relative. Well, the answer is they are. They still obey this principle that you can substitute change of acceleration for gravitational field. It's just a more complicated gravitational field than for pure acceleration. And yeah, that was one that required non-elementary knowledge of physics. So, all right, let's see. I was asking what derivative of acceleration. I think it's usually called jerk. I think the that comes up. Derivatives of acceleration are not particularly common, but it comes up in things like drones and helicopters And that's a thing that ends up being, let's think, how does this work? The issue is, if you as a human are controlling something, let's say you're making your car go faster. Okay, people understand how to put their foot on the gas and make the car go faster. But it turns out for some kinds of control, you need to be controlling the third derivative. And it's pretty hard for humans to kind of get in mind how that works. So that tends to be a limitation. It's why, for example, drones, which, have automatic flight controllers that determine, make this rotor go slightly faster so that the thing remains stable and remains kind of, as you push down one side of your 4-rotor drone, the thing will just, that rotor will be running faster and pushing you up faster. Humans find it very difficult to do that kind of control. That's why when people tried to build quadrotor devices back, in the days when they were using, internal combustion engines for that rather than electric motors now, it wasn't, you could have a human try and control it, and humans found it really difficult. And that had to do with being able to control the third derivative, as I recall. And humans just find that really hard. All right, let's see, maybe one more question, and then we should wrap this up. Lots of very interesting questions here, so I look forward to tackling them next time. The question from Frost here: do you think emotions will emerge out of intelligence? If computer scientists continue to make general AI, do you think the more general, more intelligent it gets, the more emotional it will get? It's an interesting question. So, what are human emotions? They, human emotions are kind of like, in some sense, we think about things at some rational level. We imagine, there's logic, we can deduce this from that. But then there's this kind of overlay of, and we feel this way about what we're doing. And what seems to be the case is that in our brains, there are these neurotransmitters that are the things that are actually responsible for taking signals from neuron to neuron and things like that. And different emotions probably are associated with different amounts of those different neurotransmitters. And we can kind of get a sense of that. People often make up, it was particularly popular close to 100 years ago now, these kind of charts that represent, the space of emotions. Like you can be happy, you can be sad, you can be angry, you can be content, you can be impatient, you can be patient. That maybe isn't an emotion, I don't know. You can be, there are these various kinds of dimensions on which you can plot, happy versus sad or something. You can sort of plot these emotions, and you can map those to some extent onto, the smiley faces, so to speak. A famous thing, Charles Darwin actually did this, had this book actually called The Expression of Emotions in Animals and Man. And his main observation was, we all have this emotional reaction. We're happy, we smile. We're sad, we kind of frown. And turns out, as Darwin claimed, animals like dogs and so on have similar kinds of facial expressions of what seem to be their internal emotions. And of course, that can be captured to some extent with, emoticons. You have the smiley, and you have all of those scales that, often exist of, how satisfied were you with this this customer service? Press the button from the smiley, it was great, to the frowny, it was awful. That's sort of a representation of that emotional scale. But so there's this idea that emotions are somehow on these various scales with some number of dimensions of different kind of happy to sad, this to that. And there's some possibility that those actually correspond to, in the end, to levels of neurotransmitters in our brains. There's sort of a question when it comes to animals like cats and dogs and things, maybe a lot of what is communicable, a lot of what we can recognize is emotions similar to our emotions, possibly even because it's the very same neurotransmitters that are getting different levels in the brain of the cat and so on. So a question is then, how do emotions relate to kind of the human experience? How do they relate to the kinds of things we want AIs to do? And, I think that is, to what extent emotions are kind of an overlay, like, when you have a piece of music you have definite notes that you're playing, this note, that note, that note. But then you have the sort of the instructions, play it fast, play it with vigor, play it, tentatively, so to speak, or whatever. Those are kind of the emotion script that goes along with the actual sort of play these specific notes and so on. And I think that's a similar way to the way that one might think about emotion in the context of what we're normally thinking about in terms of sort of a computational language, symbolic AI, these kinds of things. So I think that's, and when you ask the question, can you teach a computer to recognize whether that face is happy or sad? Yeah, it's easy. We have a little function called facial features that does exactly that. It can tell you, is this a happy face, is this a sad face? You can, it's easy to do sort of from the outside. How does that affect, if you have an AI and you say, okay, I'm going to give you the AI a piece of virtual chocolate, so be a happy AI. How does that then affect what the AI does? It's complicated. I don't think we really know at all how to map sort of the emotional overlay that humans use about sort of the overlay on thinking about things into the level of, so what's the answer to that computation? I mean, 2 + 2 is always equal to 4, whether you're happy or sad. But something like, it might be something like, is this a good piece of music? Well, the good piece of music, when you're in a really upbeat, really energetic, things are, mood, might be a different good piece of music from the one that's appropriate or that you consider to be a good piece of music when you're in a really, spaced out, tired, down kind of state. And so sort of mapping that stuff onto how computers should respond to things, it's not a thing that's been much done. I mean, there are various approaches. People talk about, affective computing and things, and they talk about kind of how in a user interface, for example, how, if you're talk to the robot, so to speak, talk to the bot, depending on its facial expressions and whether it seems to be happy or sad, you may respond to it differently. It's kind of the human interface may be different. If it looks like you're talking to the bot and the bot is really interested in what you're saying, and the bot is smiling a lot when you tell it this, you may respond differently in terms of how you interact with that bot. But if the question is, will sort of somehow the idea of emotions somehow pop out of kind of what we're doing in AI, I'm not sure. I mean, I think that we have to ask in biological evolution, what was the role of emotions? And I think probably emotions were an earlier form of kind of thinking in the following sense that, if you're a mouse or something and things are happening and it's like, oh my gosh, something is chasing me. It's like, I'm afraid. What do you do if you're afraid? You run away, okay? Whereas the more sophisticated mouse will say, let me consider that thing that appears to be chasing me. I believe it is a robotic cat, and that robotic cat has, motion that only goes in a straight line, and therefore I really shouldn't be afraid. I'm just working out. If I go in this place and that place and the other place, I'm just going to avoid the robotic cat and all will be good. So I kind of think that evolutionarily, probably sort of the emotions just wash the brain with serotonin or something is kind of, make it respond in a way that's it's probably sort of a lower version of what in humans ends up being sort of higher thought process. It doesn't mean it's any less real for us humans, but it does mean that it's probably something where in kind of we want AIs to do things for the sake of solving a problem of some kind that's a well-defined sort of science type problem. It's probably not really a relevant thing. When we want the AIs to interface with humans, well, emotions are a big deal for us humans. And so if we want the AIs to do things which are a good match for how humans sort of deal with the world, then the AIs have to have that capability as well. But it's sort of a capability that you're kind of, I think, it's kind of more of a bolt-on capability than a natural progression of if the AI can emulate the thinking of a human in this way and that way, then necessarily there will be some sort of emotional overlay onto that kind of thinking. I kind of suspect it's the other way around, that it's a more primitive form that it's kind of like you could teach the AI, based on this input, I should be a happy AI or something, but it's sort of an overlay and not part of the sort of detailed processes of the sort of thinking like activity of the AI. All right, well, I should wrap up here for today. And thank you all very much for lots of interesting questions. I realize, as always, as I explain these things, I understand them a little bit better myself, and I hope some of that understanding is useful and interesting to people. But thanks for joining us here, and see you another time.